Yeah. Hi, everyone. First, I want to thank the organizers for accommodating me because I had scheduled my flights tomorrow and they had to change my session. So what I'm going to present might seem a bit outside conventional robotics, but everything I use is applied in robotics. And I do have 3 slides on robots themselves. Saying that, like, what I'm interested in locomotion, and of course, I'm a roboticist, so it's always fascinating to me that the field is pushing forward, especially with like reinforcement learning now. You have like really cool state-of-the-art behaviors that it can learn in a black box kind of way. But all of this has been possible majorly because of like the new computational tools that allow for like massive parallelization and like training of these kind of models to learn control policies that can actually adapt and react. But what's also fascinating is like what biology can do, right? It's always the benchmark that we have set ourselves to reach and then also go beyond. Here is an example of like a mouse solving a maze in a natural, dexterous, and like adaptable way, where it's changing its speed, it's interacting with the environment, and also constantly solving the problems. So what I want to present is how we try to build computational models for studying biology itself. So this involves modeling the skeleton, the muscles, the nervous system, how the nervous system senses, and then the whole interaction with the environment itself, which can lead to locomotion. And of course, it's an open problem, which means there are many parameters that needs to be tuned. So you need some sort of optimization or parameter space exploration. Here is a small video of experiments that were done back in the 1900s. It's a decerebrated cat, which means the connection between the brain and the spinal cord has been cut. So and then it is being put on a treadmill and it can actually locomote. So it is an entrainment of movement with the spinal circuits that can lead to behaviors. What this has led to is modeling just the spinal cord is sufficient to have locomotion-like behaviors. And in this work, I'm going to be talking about using neural networks that are closer to biological neurons, but abstracted at certain levels. Most of the inspiration or like the modeling approach is to constantly adapt to the experimental findings. Here is an example of selectively silencing or removing certain population of neurons in the mice, which lead to an absence of certain types of locomotion. So this gives us insights into what are the specific populations that lead to specific traits, and then incorporated into models like these, where each circle is a neural population. Over the years, this has been constantly growing in terms of the architecture, where more and more experimental data has been included to show and capture all the dynamics of experimental findings and being validated. But the validation itself is at a superficial level, and there is no connection for the body. And this is where now we are trying to connect these neural networks with the bodies and actually see if we can achieve the same kind of performance. So this led to the development of the biomechanical model of the mouse, the body itself, which is based on CT scans. It's a detailed model where, like, from the skin to the skeletal properties and the muscles itself were developed. And here is an example of like a blown up view. So you can imagine this as a robot itself, that rigid body links connected together and articulated. And then we also add muscles that capture the dynamics of actuation itself. Of course, this is an overcomplex system because every muscle or actuator you add, you have additional parameters in control space. So we kind of reduce it back to a tractable system that is sufficient for like just limbed locomotion. So what this meant was we had circuits like this on the left, which had a control element for each of the limbs. So each of the yellow blocks represents like a limb control. But now that we have muscles controlling the joints, we had to add additional circuitry that controls the muscles directly. So each of these yellow blocks here has these sub-layers that actually control more muscles in the system. And of course, with the body, what we can also get is the proprioception or sensation that is now mapped back to the circuitry itself. I don't want to go into the details, but I'm happy to discuss. So what kind of, usually in a robotic system, you measure joint positions, velocities, or complete state information, while a human body or like an animal would only sense, the sensors are quite different. So it's sensing muscle force, muscle length, and velocities, and then it needs to convert into a state that it is aware. So these kind of sensations are fed back into the neural circuits as well. So what happens when you do this? Of course, it doesn't walk straight away. It tries to move, but it has no sense of goal or like movement. So it's an open network which is randomly initialized, and of course, the model falls. So this is where we need to start optimizing. Of course, the collisions are removed so the head can actually go through the ground. So the problem of optimization at some point seems obvious for a user in a high level that I need it to walk. It's the goal. And you have to tune the parameters. But when you actually look at the landscape close up, it becomes a non-trivial problem where you have multiple solutions and you lose sense of the global minimum and you get stuck in these local loops. So we try to use multi-objective optimizations. An evolutionary method here was the CMAES, which offers us to co-optimize multiple objectives. In this case, it was maximizing speed, minimizing energy, minimizing muscle activations. So you now don't have a particular solution, but you have a set of solutions which are equally valid. So you can never have like the best speed, but the best speed comes at a trade-off of either maximizing your energy or minimizing your energy. So you have a set of solutions that you can rather look at. Of course, fine-tuning a fitness function is not trivial. You end up getting like strange solutions, which are all valid, but not what we look for, but they're still valid. But I do think they're quite valid even in nature, that animals don't necessarily always walk the way we expect them to do in ideal conditions. So you kind of can imagine that there is the set of huge silly walks. But overall, generating these optimizations through generations, you can get good locomotion. And this is after fine-tuning the networks that I had shown earlier. But like I mentioned, it's a multi-objective optimization, so which means you have these set of solutions that are all different and are equally valid. So here is an example of like a faster locomotion, and here is a slower one. So it now allows us as researchers to investigate what are the trade-offs and why it chooses certain solutions the way it does. The biggest advantage of a model is that you can actually break it, which means that you can remove certain elements after optimization and see the effects of it. Here is like a side-by-side comparison of removing different sensations from the trained network, which leads to different modes of failure. So, and these can actually now be also replicated in real animal, so which is interesting also as a validatory tool for our models. And then we can also simplify things or complexify things, right? So here is an example where we freeze the forelimbs and use only the hind limbs and allow it to walk on more complex terrains. First is again an example where selectively we remove a particular feedback that completely kills locomotion. But when you connect the feedback again to the system, it can naturally get back into a walking regime. Not only that, the system is blind, but it can actually adapt because of its own body sensation to complex terrains. Here in this case, it's going over like hills that it has never seen or never been trained on, and can naturally adapt at every time step. And it can also change gaits when there is change in terrains and adapt as required to have like successful locomotion. So here in this case, you have like coordinated movements, and then there is also unsynchronized trotting. So you can really put this model through many type of terrains, and it has not been trained on it, but it can still adapt to it because of the fundamental principles. Like I said, all of these elements are translatable or agnostic to the basic framework itself. So what we are using in a computational model of an animal can also work for a robot. And I need to mention here, the robot is torque controlled, like with virtual muscles. So it has elements of biology in it as well. And below is like an oversimplified 2D model, which has its own investigative powers. But all of these elements are being used by the same network or controller architecture. And finally, I want to mention like all of this work was possible because of a framework that we co-developed with my colleague during my PhD called FARMS. And our dream is to have all sorts of virtual animals in a simulation framework that can interact, and not just animals, but also robots, because they're powerful tools. And here is an example of like some of the things that we want to put together, like from fruit flies to salamander robots, swimming, walking, and also like mice. So this is kind of like our goal, to have from primitive animals like fish to humans, all having exchange between control laws and theories, so that we can have like an ecosystem where people can go between abstractions and actually test things. So I would like to thank my lab and my collaborators for all the work that I just showed you. And of course, my lab is hiring. So if you're interested in any kind of computational work, we are in a neuroscience department, but we still do computational work. So please check us out and apply. And that's the end of my presentation. I want to end with a fruit fly simulation that we did. Because it's a simulation, we don't have any ethical limitations. So we could really go for perturbing the model here. Yeah. Thank you.